Hello. In this video, I'm going to show how to solve this problem involving a spherical conductor inside a spherical shell. The inside conductor is going to have a charge Q on it, and the outside conductor is going to have a charge minus Q. So there will be an electric field that will go between the two from plus to minus. And the first part of this problem is finding that electric field. So, part one. So this geometry has spherical symmetry. So I'm going to use a spherical Gaussian surface at radius r. So you can imagine a spherical Gaussian surface. Once again, a Gaussian surface isn't a real physical thing. It's just something I imagine that's there in between the spherical conductor in the middle and the spherical shell. Okay, so Gauss's law says that the flux, that is integral over my closed Gaussian surface of E dot dA is equal to the charge enclosed, which in my case is just Q. Only the charge that is only the inside charge is inside my surface. You know, this is my surface here. Only Q is inside of it. Minus Q is outside, so it doesn't count. Okay, so I have Q is my Q enclosed over epsilon naught. Okay, so next I'm going to use the symmetry argument. That is, the electric field is going to be the same all the way around my spherical Gaussian surface. That is, if my spherical Gaussian surface really is a sphere, not this jaggedy thing I just drew. So because the electric field will be uniform, we can pull it out of the integral. Why is it uniform? Well, by symmetry, it'd be really weird if there was more field coming out of one side of the sphere than another side of the sphere. After all, it's a sphere. Which side? There's no preferred side. So I can pull E out. I get E, the integral dA is equal to Q over epsilon naught. Integral dA is just the area. What is the surface area of a spherical Gaussian surface? Well, E times 4 pi r squared. The surface area of a sphere is equal to Q over epsilon naught. And we find E is equal to Q over 4 pi epsilon naught r squared. Interestingly enough, that is the same answer as for a single charged point charge. So the fact that the inside has a radius makes no difference. It's all inside the Gaussian surface. So whether it's a point charge or an extended ball of radius r, doesn't matter. Also, the outside shell doesn't matter. It doesn't affect the inside. Okay, so that is the electric field, and it points outward if we want to make it a vector. Okay, let's do the next part of the problem. And the next part of the problem asks, what is the voltage difference between the two conductors? And I'm going to do this by a integral. So you may remember that the voltage difference, delta V, is equal to the integral from one point to another point of E dot ds, the path integral. This is basically saying, field points downhill. If you integrate downhill, sorry, there should be a negative sign there. You get a voltage difference. Okay, so in my case, what path am I going to use? I'm going to take the path from the inside directly to the outside. So I'm basically going to integrate in the radial direction, which is going to be really nice because the electric field points in the radial direction, and I'm traveling. My ds will be dr because I'm basically traveling along a radius. So I can change this to V final, which is V outside, out minus V in is equal to E, the integral minus integral from R in to R out of E dr. And I don't need to worry about the vectors and the dot product because the E points in the radial direction and R points in the radial direction. So they point in the same direction. So the dot product gives you cosine of 0, which is 1. So that's good. We got E dr. Okay, so now we can just stick in. I'm just going to refer to this as delta V. And I'm actually going to delta V. I'm going to define delta V as V in minus V out. Why do I do that? Well, the inside conductor is the positive one. The outside is the negative one. So it seems going to be, I mean, this is just a sign convention. I'm picking the voltage difference. I'm going to assume the inside, well, the inside is going to be a positive voltage. The outside is going to be negative voltage because the outside has the negative charge. The inside has the positive charge. Okay. So I'm going to define my delta V as V in minus V out. So that's what I'd be like negative that delta V. V in minus V out. So that'll simply be the integral from R in to R out of E, which is Q over 4 pi epsilon naught R squared dr. Doing this integral, you will find that delta V is equal to Q over 4 pi epsilon naught, and then the integral of 1 over R is minus, or 1 over R squared is minus 1 over R. And then you stick in the limits and flip it and do some more algebra. I'll let you do that yourself. You get R in minus 1 over R out, like so. So that is the delta V. And then finally, the last question that it asks us about is, what is the effective capacitance of this spherical capacitor? So number 3, by definition, Q equals CV, or the definition of capacitance is the charge per voltage. So we can say the capacitance of this capacitor. Now, this isn't a parallel plate capacitor like the ones we're used to. This is a spherical capacitor, but it's kind of like a parallel plate capacitor. You have two conductors that are separated by distance. They just happen to be a sphere instead of two plates. So capacitance is equal to Q over V, which is Q over 4 pi epsilon naught 1 over R in minus 1 over R out. We can do some algebra to that, simplify it. We get C is equal to 4 pi epsilon naught R in R out over R out minus R in. And that is the capacitance of a spherical capacitor. And that completes this problem.